Today I'm going to be explaining the quicksort algorithm in an equally quick and easy way. Quicksort is one of the leading sorting algorithms used in the industry because of its spatial and temporal efficiency, especially as the arrays get larger and larger. In order to explain the algorithm, we will be using a small 10-element array as an example. The first step in the quicksort algorithm is to find a pivot number. There are several ways to do this, like by selecting the median of the array, but for simplicity's sake, we will just select the last element in the array, which in this case is 5. The next step is to partition the array. We will split this array into two sides, with the left side consisting of elements smaller than the pivot, and the right side consisting of elements greater than or equal to the pivot. In order to do this programmatically, we will need to go through the array and compare every single element to the pivot. First, we will compare the first element of the array, 2, to the pivot. It's smaller, so we leave it on the left side and continue. 7 is greater, so we move it to the right side. 3 is smaller, 0 is smaller, 1 is smaller, 8 is greater, so we move it, 5 is equal to, but as we explained, the right side of the array will contain elements that are greater than or equal to the pivot, so we will move this 5 to the other side. 9 is greater, 6 is greater. There. Now all the elements have been partitioned. However, this array is not sorted. What do we do next? Consider our pivot number 5 here. This 5 is, for all purposes, sorted, because the elements on the left are smaller, and the elements on the right are greater. The subarrays themselves may not be sorted, but they will only change places within themselves, never within each other, so the 5 will never move from this position. We can therefore lock in this 5 as a sorted element, and deal with the subarrays separately. Obviously, we will be using quicksort again on these subarrays. We will use the same pivot selection technique as earlier, and just choose the last element in each. In that case, those will be the elements 1 and 6. Now, this algorithm will repeat. Since we have already gone through an iteration of quicksort, I will fast forward through this process. Our first iteration, which we went through before, second iteration, third, fourth, and the fifth and final iteration, which leads to this sorted array completely. You may have noticed that the array was sorted back here, 3 steps before the end of the algorithm. Why don't we add a check after every iteration of quicksort to see if the array is fully sorted already? Then we can catch things like this and end early, saving time. Unfortunately, this wouldn't fly in a real example because the array would be much larger, and it would be extremely inefficient to have to run through the entire thing after every cycle. So the quicksort algorithm will go all the way to the end. Moving on, we will look at the runtime of this algorithm in separate cases. We will assume that we have an array of size n, because that is the standard for big O notation. In its worst case, we will run through these following quicksort steps. Our first partition of the array will split our array into 2 subarrays of sizes 1 and n-1. This is achievable if the pivot that we select is the smallest or the largest element of the array, which will put it at either the beginning or the end of the array and leave the rest as the other subarray. This pattern will continue, with the next partition leaving 2 subarrays of sizes 1 and n-2. This repeats again and again until the end, when the last partition splits it into 2 subarrays of sizes 1 and 1. To calculate the runtime here, we will see how many comparisons are made. The first iteration has n-1 comparisons, because the array is of size n, and we compare every element that isn't the pivot to the pivot. The next iteration has n-2 comparisons by the same logic, all the way down to 1 comparison on the last iteration. This is equivalent to a summation from 1 to n-1, like so. Plugging in into the summation formula, we get n-1 times n-2, which can be simplified to n squared, because we can eliminate constants in big O notation. Therefore, our final worst-case runtime is on the order of n squared. Next, we will look at the runtime for its best and also its average case, which are the same for this algorithm. Again, assuming we have an array of size n, we run through the following steps. The first partition splits the array into 2 subarrays of equal size. The next partition splits those 2 subarrays again into equally sized subarrays. This continues until the end. To calculate this is a little trickier. Notice that in every iteration of quicksort, we utilize some portion of the elements for comparisons. This means that per iteration, we have some order of n comparisons, because n is a maximum number that we could use for comparisons, and we only take a part of that. Now, how many iterations do we have? Since each iteration halves the size of the array, we have log 2n iterations. Combining these two, we will have a total runtime on the order of n log n. The proof for why this is the same runtime for the average case of this algorithm is too long for this tutorial. But in essence, a good pivot finding function, like by using the median, will result in relatively even partitions, similar to the best case here. That's all for Quicksort. Thank you for listening.